the duration of the lecture. We encourage you all to ask questions during the lecture, but please do so in the chat. One of the organizers will communicate your questions to the instructor. You will also have an opportunity to ask questions verbally at the end of each lecture. With that being said, we are very excited to have Rose Morris-Wright, who will be speaking about Artin groups, algebraic and geometric techniques. Take it away, Rose.
All right, thank you very much. Thank you for having me. I'm so excited to be here for this wonderful mini course, or it has been wonderful so far. I hope I add to it. All right, so I'm going to talk to you about Artin groups today. So let's just jump right in with our definition. What is an Artin group here? So I'm going to start with gamma, a finite simplicial graph. So finite means there's a finite number of vertices, and simplicial means there's no edges going from one vertex to itself, and no multi-edges. Excuse me. And so we're gonna label the vertices of this graph. The vertices we're just gonna label them with this set S. So these are going to be the generators of our group. And then I'm also going to label the edges. The edges are labeled with integers, which we call Mij. So Mij is the label between Si and Sj. And these are integers greater than or equal to 2. So I have 2, 3, 4. They can be as big as we want. And then if there's no edge between Si and Sj, we say that Mij is equal to infinity, just as sort of notation there. And then this graph is going to help us encode a group presentation. So the Artin group, which we denote A sub gamma. This is equal to the group with the following presentation. So the generators are the sets S, and the relations are determined by the edges. So I'm going to have Si, Sj, Si, right into this alternating pattern will be equal to Sj, Si, Sj, alternating where I'm starting with the other one first. I'll do an example of this in a moment. And each of these is length Mij terms here. And here you also have Mij terms. So let me do an example here. Here's my example. Let's just do a pretty simple graph here. Maybe I just have 2 edges. And my vertices are S, T, and R. And maybe I have, 2 and 5, something like this. Right, and so this is the group. It's generated by S, T, and R. And the edge labeled 2 gives me a commuting relation. So I have ST equals TS. And then the edge labeled 5 is going to give me this TR, TR, T equals R, TR, TR. Right, and each of these words has 5 letters in it with this 5 right here. And then there's no relation between S and R because these guys are Mij equals infinity. So this is the kinds of groups that we're going to be talking about for the whole mini course. It seems pretty simple, just this presentation, but it turns out there's actually a lot of complicated stuff that comes out of this. Let's do some more examples. So you can have free groups, right? Free groups are when gamma has no edges. You can have free abelian groups. All right, that's when all of there's edges it's a complete graph, edges between all of the vertices, and they're all labeled 2. Also, one of the prototypical examples here is braid groups. Right, so braid groups have commuting relations, and then they also have this like STS equals TST. This is a very typical relation you might find in a braid group. So sometimes these are actually called generalized braid groups because of that sort of idea, right? So these are also called, they're also called Artin Tits groups. I should capitalize this because it's a name. So they're first defined by Tits in 1966, and they're also sometimes called generalized braid groups. Let's say, AKA generalized braid groups. And this is the notation that I'm going to be using for all of our mini course. I do want to say that sometimes you see other notations if you look this up in the literature. So sometimes you'll see like instead of encoding all of these Mij in a graph, you'll encode them in a matrix, right? So it's a little bit like the adjacency matrix of the graph. Sometimes you'll make a graph like here, you'll notice I'm drawing all the edges where there are relations, and I'm not drawing edges where there's a free relation. Sometimes you want to do like if I'm studying groups where free relations are relatively uncommon, you might want to just make some other sort of convention, right? So maybe you draw all the edges that are labeled 3 and greater, and you label some of them by infinity, and then when there's no edge, that represents commuting, something like that. So there's just so you know, there's other notations out there if you go and look at this in the literature. All right, so just a little bit on let's just say our goals for our talk, for our mini course. So my main goal, like for today and for the whole course, is to show you that there's lots of actually open questions about these groups, and to give you a little bit of a sense of where the current research is and what people are still trying to figure out. So for today, I'm going to talk about different types of Artin groups. So this we've learned about like the most general overarching class, and then there's lots of different little subclasses inside. The most famous one is right-angled Artin groups. You've probably heard of those, but there's lots of other different types of Artin groups, and then we're going to talk about some open questions, and most of these are questions that have been solved for all the different little types, but are open in general. There's really very little that we know about the class of Artin groups altogether. So we're going to talk about that. And then tomorrow and Friday. So tomorrow is going to be like algebraic questions. And then Friday will be geometric questions. But I'm still kind of trying to focus on questions and giving you ideas of where current research is sort of pointing and trying to figure out things that we don't know about. So that's the plan. I hope you guys are excited for the plan. All right, so first, maybe let's just do a little bit of motivation about why we might want to study these groups. And in order to do that, we need to define their cousins, the Coxeter groups. So the Coxeter group, which we denote W gamma. So gamma is the same, it's my same simplicial graph. And W gamma is going to be my Coxeter group. And I'm going to have my same generators, and then I'm going to have the same relations as above. And then I'm also going to add this relation that all of the generators are ordered 2. So I took the exact same presentation and I made all of my generators into, you can think about them like transpositions or reflections, right? W here is for Weil groups, right? Coxeter groups are very much the more well understood cousins of Artin groups. You see Coxeter groups all over the place in Lie groups and various, representation theory type, like Coxeter groups are of interest to people outside of geometric group theory. Let's do some examples here. I think that the key example to sort of understand this is, so if I have A gamma is a braid group, then W gamma will be the symmetric group. For the same gamma here. So like maybe one element of my braid group is, something like this. Here's my little braid, right? So this is telling me I have strand 1, 2, 3, 4, 5, and this element of my braid is telling me I cross 4 over 5. And if I forget about the fact that I'm twisting and I just think about this as a permutation, right? So my corresponding symmetric group element would just be the, 3, 4 transposition, and everything else stays fixed. And you can really think about, Coxeter groups and Artin groups in general working this way. Like I took all of my generators and I just forgot that they were, I'm forgetting some information. I'm forgetting that they're infinite order, and making them all order 2, right? So this is a transposition. So maybe let's just do some other examples here. You can also have other examples of Coxeter groups, like so the infinite dihedral group is a Coxeter group. Weil groups of certain Lie algebras are Coxeter groups. Right, so a lot Coxeter groups come up a lot when you're thinking about reflections and that kind of thing. So that's sort of the definition of Coxeter groups. And then what's one of the main ways that Coxeter groups and Artin groups are related is through this geometric space called the hyperplane complement. So the idea here is that every Coxeter group can be constructed as a group of reflections, let's say, acting by reflections on a vector space. This doesn't have to be a Euclidean vector space. It could have some kind of wacky inner product on it. But I'm going to do an example here. So my example here is the easiest one to draw, which is gamma is going to be a triangle. And all the edges are labeled 3. Let's give these STR. And then I think I actually have a picture here. Hold on. Yeah, here we go. So here's this picture. Let me make it a little bit bigger for us. So this is the Coxeter group acting on the Euclidean plane, right? I've tiled my whole plane by triangles. And then you can think like, okay, here's my identity triangle, right? This is like staying fixed. And then when I reflect about this line, that's like acting by T, right? And I move my identity triangle over here to my T triangle. And when I move my identity triangle over here to my T triangle, here, maybe I should do some colors here, right? So like if here's the purple edge of this triangle, and then when it gets flipped over the T, this becomes a purple edge, right? So reflecting up from my identity triangle to U here, I guess, sorry, in this picture, I'm ST and U instead of ST and R. But it doesn't really matter. So when I start from my identity triangle, I can either reflect over here to T, or I can reflect up here to U. And then when I do go over to T, I can then reflect over the image of my U line over here, and I get to UT. And then I can reflect by T again, and I get over here to TUT, right? So this, and here I have this, let's draw it like this. So here I've reflected by T, I've reflected by U, I've reflected by T again, and that's going to be the same as reflecting by U, reflecting by T, and then reflecting by U again, right? So here I've got this TUT equals UTU. This is this square, this triangle right here. So you can sort of see these Artin relations in this kind of picture. And you can do this for any Coxeter group. This is the easiest one to draw because it's it's acting on a nice Euclidean plane here. But you can have your vector space be spherical, right? And maybe you're tiling a sphere and you're reflecting around inside a sphere, or you can put some sort of other inner product. You can have, many dimensional vector spaces, right? So if you let your vector space be whatever, you can do this for any Artin group. And then the point here, so first of all, I've just got my Coxeter group in the picture so far. And then the idea here is my Coxeter group has a group action on not only on this vector space, but on what is usually denoted H gamma, which is the complexified hyperplane complement. So the idea is I took this vector space and I chopped out all of these hyperplanes, all of these reflection planes. And then I had just a disconnected collection of a bunch of triangles, and I want a connected space. So I complexify it, and now I'm acting on a connected space. And this is great because then what do I get? I get that the Artin group is equal to the fundamental group of the hyperplane complement modulo this action. So this is one of the reasons to study Artin groups, is that they are telling you about these hyperplane complements, right? They're telling you about like the homotopy theory of these hyperplane complements. And so I told you I was going to tell you lots of open questions. This is like one of the biggest open questions is called the K-pi1 conjecture. The K-pi1 conjecture says that this hyperplane complement modulo my action by my Coxeter group is a classifying space for my Artin group. In other words, so the Artin group is equal to pi1, which we know is true, and then the open part here is that pi n of this space, right? The higher homotopy groups. I want these all to be trivial in order for it to be a classifying space. And this is one of these questions that I was just mentioning, which I'm going to give you more detail about. But this is a question that's known for different types of Artin groups, for very specific types, and that gives us good reason to believe that it's true for all Artin groups, but it's open in general. So this is one of the sort of exciting, but very difficult questions. Right? People have been thinking about this. This is like has been open for 50 years type question. So maybe this is a good place to pause. Are there questions that I should?
There is a question, Rose. Can a group be an Artin group with respect to two different graphs, non-isomorphic graphs?
Yes, that's so. Yes, well, that is one of the open questions is when exactly does that happen? But there are examples when you can have two graphs that make an isomorphic Artin group.
Okay.
Yeah, good question. All right, maybe let's move along here. So next I want to talk about different types of Artin groups. So as I said at the beginning, most of these questions have been answered for particular types of Artin groups. And like there are types of Artin groups that we know a lot about, and then we know basically nothing about all Artin groups. So I want to tell you a little bit about what the different types are. So the first type that I want to tell you about is called finite type. Or sometimes it's called spherical type. And these are Artin groups, A gamma, such that their corresponding Coxeter group is a finite group, meaning it has a finite number of elements, right? So for example, braid groups are a finite type Artin group because their corresponding Coxeter group is the symmetric group, and symmetric groups are finite groups. This example that we just did up here, right? This is an infinite type group, right? Because you can see I have infinitely many triangles in this tilation, so my Coxeter group is going to be infinite. All right, so and they're sometimes called spherical because these are exactly the groups where this vector space is a sphere. So that's or has an inner product on it that makes it have a spherical metric. All right, so that's one type. Another type is the right-angled ones, which if you've heard about Artin groups before, you've probably heard talks about these, right? So these are all Mij equal to or infinity, right? So every relation is either a commuting relation or a free relation. Usually people don't even bother to label the graphs for these, right? It's just like there's an edge if it commutes and there's no edge if there's a free relation. And these are very well studied. These are examples of cat zero cubical groups. So you guys had a lesson about cat zero geometry earlier. So these are an example of groups that act geometrically on a cat zero cube complex. So everything that we love about cat zero cube complexes you get about these groups, and as a result they're very well studied. But this also means that like the techniques that you use for studying these are pretty different from the techniques that you use for studying more general Artin groups, just because this cat zero cubical stuff gives you such strong tools that you don't have for the other Artin groups. So I'm not going to talk too much about those, but just so you know that they're out there. And then some other types of Artin groups. Maybe let's here's another piece of notation for you. So if T is a subset of my generating set S, then I denote by A sub T. This is equal to the subgroup generated by T. And there's a result. This is by Vanderlik in 1983. This is his PhD thesis. That says that this subgroup is isomorphic to the Artin group that's just generated by the subgraph of my graph, right? Where gamma T is, let's say, the full subgraph spanned by T. So the idea is here I can take a subset of my generators and I can look at the subgroup that's just generated by those, and it turns out that's actually an Artin group. It's exactly the Artin group that we expect it to be, which is great. And then once we have this notation, we can define a third type of Artin group, which is FC type. So an Artin group is FC type if all complete subgraphs, right? So all cliques, right? All subgraphs that where I have edges between all of the vertices generate finite type subgroups. Here's an equivalent definition. The FC type are amalgamated products where you can construct this amalgamated product out of finite type pieces. So in terms of the history, there's a little bit of first, when people first started studying Artin groups, they very much first started looking at these finite type ones. There's here, maybe I have some references I should put in here for you. Like if you want to know about finite type, like so Tietz in his first 1966 paper spent a lot of time talking about finite type. There's also a nice paper by Brice, Korn, and Saito. This is 1972. Deline in 1983. Charney in 1992, right? So there's, sort of, in this time period, lots of people are studying finite type Artin groups. They're mostly using algebraic techniques, which I'm going to talk about a little bit tomorrow. What's called the Garside structure. Basically, finite type, it turns out, behave very similar to braid groups, and a lot of the techniques that we have for braid groups just carry over straight to finite type, and that was really useful. And then people started, studying right-angled ones and using cat-zero geometry, and so that became a whole field. And then the FC type ones sort of started being studied mostly by Charney and Davis in 1995, and Charney and Davis have a way of constructing this geometric space that helps us take information about these finite type subgroups and extend them to these amalgamated products. So that's what I'm going to talk about on Friday, or whatever day, Thursday, third lecture of our mini course. So these are various different types, and a lot of what we're doing is building taking these groups that we know things about and trying to build larger and larger groups out of those, and see if we can get more and more general results. But still, we don't know about lots of things. Maybe other types I should just mention here. Other types that are out there. There's also 2D Artin groups. There's large type Artin groups. Those are where all the labels are. There's no commuting relations. All the labels are greater than 3. There's even type Artin groups, right? So all the labels are even numbers. There's Euclidean type Artin groups, right? So I could go on and on and on, but I'm not going to. I did want to mention what I call this the monster. I think that might be a personal term by me, but I just wanted to point out an example of right. So here's my graph. It's a complete graph, and all the labels are 3, except one of them is 2. And I just wanted to point out this is none of the above. This is not finite type, it's not right angled, it's not FC type, it's not 2-dimensional, it's not large, it's not Euclidean, it's none of these, right? This is an example of the kind that we know absolutely nothing about. And it looks pretty simple on paper. So this is when I say, general Artin groups, we have these open questions. These are the kinds of groups that we really would like to study. So I should tell you what some of these open questions are. Right, so here's results and open questions. So let's just, so all of the following are known for finite type and right angled and FC type, etc., but open in general. And we're going to make a little list here. So the first conjecture is that these groups are what's called automatic. Right, so in particular, that means they have a solvable word problem. Right, so given a word, given a collection of or a list of these generators, there's a finite time algorithm that I can apply to this word to figure out if this word represents the trivial element in the group. Similarly, it means there's a solvable conjugacy problem. Right, so there's a finite type algorithm that will help me figure out if 2 elements are conjugate to each other. And in fact, so part of this, things that are known for all of these nice types up here, but open in general, it would be really great if there was a nice canonical form for an element. And you can see that in the finite type ones, in the RAGs and the FC types. All of these have a way where I can take a word and I can apply some sort of algorithm. It might be like a left greedy algorithm where I'm like moving all of the letters as far to the left as I can in some sort of way. And I have an algorithm that I can do this, and eventually my algorithm stops and it produces a unique word for each group element. So this is one of the nice conjectures that's out there, and again, open in general. I already mentioned the KPi1 conjecture, but I should add it to this list. Right, so the KPi1 conjecture, right, this says that the hyperplane complement is a classifying space. This is known for finite type groups. That was one of the reasons that we first started studying Artin groups. And it's known for right-angled Artin groups. It's known for FC type Artin groups and 2-dimensional and all of these others, but very much open in general. Okay, here's one that I found kind of surprising when I first found it out. Torsion free. We conjecture that all of these groups are torsion free, right? They have no elements of finite order, no elements where I can multiply that element by itself a finite number of times and get back to the identity. This is very much true of braid groups and finite type groups and all of these nice types, but not true in general. Here's another. The center of the group, right? So the collection of elements that commute with all of the other elements in the group is Z or some product of Z if I'm a finite type group, or if I'm a product like, a direct product, I should say, with at least one factor finite. So finite type groups are we know exactly what the centers are. There's actually a nice element that generates the center of an irreducible finite type Artin group. That you can think about, if you know about braid groups, you can think about like the half twist is this element in braid groups. We'll talk about that more tomorrow.
Sorry, the last two elements are conjectures,
yeah. So these are both things that are known for finite, for regular, for various types of Artin groups, but not for Artin groups in general.
Like okay, so the last one is known for finite type, you're saying, but the center is either 0 or 0.
Yes, yeah. So it's known for finite type and for products of finite type, and then the conjecture is that it's trivial otherwise. I should finish writing this down. So the idea here is we know exactly what the centers are for finite type. And then, when I take products of finite type, I know what the center of a direct product is. That's clear. But then the idea is, the conjecture is that that's the only way for me to get a central element in an Artin group. And this is known in right-angled Artin groups. It's known in FC type Artin groups. But again, this is open in general. Let's see. Other questions? Maybe this is a good pause point. All right, good. Yeah, so these are a list of things, as I said before, that are known for particular types of Artin groups, but open in general. Maybe I'll just say, okay, here's a nice theorem. This is by Godel and Paris, originally in 2012, which says that, so if the above conjectures are true, for all A gamma, where gamma is a complete graph, is a clique, then they are true in general. So in some ways, this says, I've been talking about how these are open questions for all Artin groups. We don't really know any of these things for all Artin groups, and this gives us a nice way of zooming in on exactly the Artin groups that we really want to study. Notice that one that this one up here, this monster that I was talking about earlier, right? So this is an example of a complete graph. Right, so this is exactly the type that we would really like to figure out all of these questions. And once we figure out these questions for this type of graph, right, where I have a relation between all of the generators, but it's not necessarily falling into any of these other categories, then we would be in business for everything. But that's proving difficult. All right, maybe here's some other open questions. So someone was asking me earlier about can I have two graphs that are different graphs that produce an isomorphic Artin group? So this is one of the important open questions. This is called the isomorphism question. Right, so if A gamma 1 is isomorphic to A gamma 2, does that imply that gamma 1 is equal to gamma 2? And this is something that's similar to the things that I've said above. We have some partial results. So this is true for finite type groups. This is by Paris in 2004. This is one way that Artin groups are different from Coxeter groups. This is maybe I'll just write that here. This is false for finite Coxeter groups. So there are examples of graphs where the two I can have two graphs that produce different Coxeter groups but the same Artin group. So Artin groups are in some sense more rigid than Coxeter groups. You can think about it that way. This is also known. So this statement is true for even Artin groups, right? So for all Mij equals an even number. This is by Paris and Blasco Garcia. This is a very recent result. I think this is last year or maybe even this year. So that's very exciting. Unfortunately, we do have some counterexamples. Okay, so here's a counterexample. Here's two groups that produce two graphs that produce the same group or isomorphic groups. I'm going to have something like this. And then I'm going to have the same triangle on top here. And I'm going to switch the order of the 6 and 7 like this, right? So these produce the same Artin group. I should give you a citation for this. This is Brady and McCammond and Mueller and Newman. In 2002, they discovered this counterexample. And so now the conjecture is, is this the only way to produce produce examples like this, right? Like, so maybe I should write that. New conjecture. Are all examples of gamma 1 not equal to gamma 2, but a gamma 1 isomorphic to a gamma 2 of this type, right? So they actually in this paper they actually have a very concrete way of defining what they call I think they call it a twist, which is what they're doing when they sort of interchange the labels on these two lines. So the conjecture is that this is the only way to get counterexamples like this, but this is very much open.
Sorry, can I ask this?
Yes, go for it.
And also there's there's a question in the chat that's part of mine. So is it known, for example, that the graph itself, the underlying graph, has to be the same for the?
I don't think so. Yeah. I mean that is part of this conjecture, right? So all of these flips are where I just move the labels around, and it has to do with the fact that this number in the middle is odd here as well. Like when you the fact that this number here is odd means that there's an element that you can conjugate by that will permute these two generators right here, and so that's part of how you're like getting this flip. And yeah, it certainly wouldn't surprise me if it was true that the underlying graphs had to be the same, but I don't think that's known. All right. Okay, so this is one of the open questions. And then the last set of open questions that I thought I would talk about for today is questions about hyperbolicity. So all of these questions are the same flavor. They're also what hyperbolic, let's call them hyperbolic like spaces do Artin groups act on? So first of all, you might ask, are Artin groups hyperbolic groups, or which Artin groups are hyperbolic groups? That would be really great, right? It turns out they're not, right? So only free groups are honest to goodness hyperbolic groups, right? Groups that act geometrically on a delta hyperbolic space. And I think I actually put this in the exercises. So you guys can prove that. Then you might ask, when are they relatively hyperbolic? Right, so when are they hyperbolic with respect to some subgroups? And this is known. This is proved by Burstock and Drutu and Mosier in 2009. And they say that Artin groups are relatively hyperbolic if and only if they are freely decomposable. Right, so if my Artin group is actually a free product of two smaller groups, then it's going to be relatively hyperbolic with respect to those smaller groups, and otherwise it's not. And then we might also ask, when are they acylindrically hyperbolic, right? That's what you spent all morning thinking about. So let's think about that a little bit. So this is, again, this is one of those things that we don't know for all Artin groups. We know it for certain types, right? So this is known by Chatterjee and Martin in, I didn't write down the date. I think it's 2017. It's somewhere in the last 5 years. So A gamma is acylindrically hyperbolic if it is FC type and the diameter of the graph gamma is greater than or equal to 3. And then there's some other partial results here. Charney and myself, actually. This was in 2019. A gamma is acylindrically hyperbolic if this graph gamma is not a join.
So sorry, the last two results assume finite FC type.
This one does. This assumes FC type. This one is just in general.
Okay, and does the first one assume something that you're not a complete graph?
It assumes that the diameter of the graph is greater than or equal to 3, right? Maybe I should define diameter of the graph, right? The diameter of the graph is like if I have vertices, right? I need to have a geodesic path between vertices that's at least length 3. So it can't be a complete graph for sure. Yeah, and this one down here, right? So not a join implies diameter greater than 2, right? So this is a stronger result, but still not quite as strong as we would really like, right? This, like, what we would really like to say here is something like they're asymmetrically hyperbolic if they're not direct products of smaller Artin groups, right? If I'm a direct product if specifically if I'm a direct product where one of my pieces is finite type, then I'm not going to have trivial center. I can't possibly be asymmetrically hyperbolic. Asymmetrically hyperbolic groups have trivial center. So we would really like to say something like A gamma is acylindrically hyperbolic if it's not, a direct product or something like that. And graphs that are joins are depending on what the labels of all of the, right? What do I mean by join? Maybe I should say that. Right, so a join is where I've got two collections of vertices and all of the edges are, right, all of the vertices in this collection are connected to all the vertices in this collection. And in our result, you can have any label you want on all these middle edges, which is part of why it's not quite as strong as we would really like it to be, right? We would like to say something like, if all these labels are 2, then it's a direct product and it's not asymmetrically hyperbolic. And if all these labels are not 2, or if at least one of those labels is not 2, then it's not. But we don't have that. But there's also, another interesting direction. This is by Calvis and Wiest in 2020. So if I take a finite type group and I mod out by its center, so we already talked about how we know the center of a finite type group. This is going to be acylindrically hyperbolic. And this is not super surprising. This was known for a while about braid groups. Braid groups are acylindrically hyperbolic when you modulo out by their centers. And they're just extending those techniques to all finite type Artin groups. But there's definitely that's another interesting question is what happens when I mod out by the center of an Artin group? Is it going to behave well with respect to this this acylindrical hyperbolicity? Of course, as I mentioned before, it's conjectured that many of them have trivial center. But this is the way that you get around that if you're working with finite type. And then the last open question that I wanted to mention to you today is are these groups cat zero, right? So when does A gamma act geometrically? Co-compactly, properly, and by isometries on a cat zero space. It would be great if it was a cube complex, but I'm not even insisting on that, right? And so what are the known things? The known things are that rags, for right-angled Artin groups, yes, as you probably know. And then other than that, it's entirely open, right? This is in fact, I believe it's still open for at least some braid groups, right?
What if you relax the geometric action? Do we know when they act on Kaiser cube?
I'm going to talk on Friday. Maybe I'll say this in a different color, right? So there are examples, in particular FC type, but also others. In fact, is this true for all Artin groups? Yes, never mind. This is true for all Artin groups. For all Artin groups, you can construct a cat zero cube complex, and they act co-compactly, but not properly. In fact, for many Artin groups, this cat-0 cube complex turns out to be finite diameter, right? So it's, in terms of its large scale geometry, it's just like a little ball, and it doesn't actually tell us anything. But yeah, you can get this sort of co-compact action pretty easily. But it's the properness, right? Having all of these examples, and I am going to construct this space for you on whatever day that is, Thursday. So that's a nice little preview. But this is, they have very large the vertices have very large stabilizers, and in some cases they have a vertex that's stabilized by the whole group even. So it's not always useful. Sometimes.
Is it known when this action is like a little nicer, like that you don't have such that everything is fixing everything? Like,
this action is always not proper, right? It's always going to have, I guess.
Yeah, not proper. But
yeah,
like,
even. I'm thinking about, like, even in the free group case. I guess maybe in the free group. No, even in the free group case, it's going to have vertices that are generated by, so that your preview for Thursday, this has vertices that are stabilized by these A sub t, where t is a subset of S. And there's some conditions on this T, and you can make different versions of this complex varying depending on which T you allow here. But you always at least have like if I have a single vertex S, then I might have like the subgroup just generated by S, right? This is an infinite cyclic group, and it's going to stabilize one of the vertices no matter what, pretty much. So it's always going to be not proper, unfortunately. I think that's all I have for today. So tomorrow I'm going to talk more about finite type groups. I'm going to talk about some of the algebraic techniques that we use to study finite type groups, and then I'm going to talk a little bit about parabolic subgroups, which are subgroups that look kind of like this, and how we can use them to study Artin groups.